and I'm hosting this session, but I'm also one of the presenters today for this first session, Fundamentals of IP in Broadcast Production. I'll be joined by my colleague, Ed Calverley, and we'll be spending the next 90 minutes running you through a lot of the basic technology that supports IP in broadcast, ST2110, and lots of other topics. So I wanted to let everybody know that we will be recording this on video. We will be posting it to VSF.TV as well as the VSF YouTube channel within the next few days or so. And you'll also be able to get a copy of the presentations and other information in PDF form. Make sure that you scan your badge at the front entrance, and you'll get information about where that information's located. Just to introduce myself, I'm president of Telecom Product Consulting, independent consultant primarily focused on technology, specifically market outreach, as well as training. My associate Ed Calverley, president and founder of Q3 Media Training, and also very skilled trainer, so we're hoping to give you a good session this morning. So let me just give you a little bit of a run through of how we're going to organize things. It's going to be the Ed and Wes show. So Ed will start out with the IP and networking basics. Then I will dive into ST2110, all the different flavors of that. We'll go back to Ed for some talk about timing and synchronization, cover a few small topics that are very important in IP video, 2110-21 traffic shaping, the new parts of 2110, 2022-7 redundant transport, and then one ring to rule them all, the NMOS sessions, the NMOS technology that's going to be used for control and monitoring and all the other good things you need in order to have a real live production network. So without further ado, I'll turn it over to Ed, and we'll go from here. Thank you.
So networking, or IP, and why IP, and it is, as I said, you've probably heard these arguments before. There's kind of two main drivers. The biggest driver really is the flexibility that IP gives us, particularly in this kind of move to 4K and potentially what might come in future. Will we have HDR over HD and all these different formats? With IP, it gives us that flexibility of being able to change for whatever comes next. Once we've got that IP infrastructure in there, we can put different signals over it. What we can also do is rearrange where we're putting people. We can make more use of software and soft control surfaces so that we can rearrange how our broadcast facility works rather than having to run SDI cables everywhere. So it gives a lot more flexibility in that. The other thing that people like to think of as the driver for IP is, of course, cost. They think that somehow IP is going to make things cheaper and whizzy, and actually it just moves the costs around. I think it's fair to say with the move to IP, things are moving certainly to a more OPEX-based model where you're paying software as a service type models and pay for what you use. So possibly over the lifespan of a project or the lifespan of a system, it may be cheaper to run longer term, but the costs are just in a different arrangement. In fact, the upfront costs of an IP system, because you're having to put in lots of new switches, they can be comparable. So certainly I've seen a lot of projects where they're just expanding SDI infrastructure because they're not quite ready to jump into the big IP step yet. So it all has to be kind of weighed up. The other big thing that you'll hear talk about is COTS. Now, what is COTS? Firstly, let's think about where most projects have been up until now. Broadcast is a very proprietary system. Lots of people have very custom-built software, custom-built systems. There's lots of broadcast vendors who count their customers on one hand. They have a system and they have a few customers, and that can be still a big broadcast company. As we move to COTS, what we're talking about is off-the-shelf things that we can buy, more turn the handle and get it delivered. Typically, the prices are listed on the website. We're talking about standard IT hardware, like HP or Dell servers. typically in those cases, manufacturers who are moving to more COTS kind of models, they're expecting their product lines to have a longer lifespan, they're expecting them to be more stable, but it does mean that you as the user may have to accept that there be less flexibility, or you may not get it quite how you want it, you'll have to do it how the manufacturer's kind of given you the options. You've seen it all on your web, on your phones, that the amount of options are kind of diminishing. So COTS is not always going to give you the flexibility you expect, but that's kind of where it's coming from. It's also fair to say that not all IP hardware is equal. I think that's going to be very evident by a lot of the presentations we see at this show. Adherence to standards is one thing, but it's also about the performance of the systems and understanding where things can fall apart. So it's definitely important to get good system architecture in there. And kind of this one I kind of already covered. Software is the big thing. The new standards that we're looking at for 2110 and things have to work in an environment now where we're using a lot more software. So they've been designed to work for both hardware-based devices and software-based devices. Software is only going to get more and more as we move to kind of hybrid cloud models and things like that. So you're going to see a lot more software. So IP, fundamentally, it's all about packets. Now, where we've come from in the days of SDI, SDI was a continuous signal. When we talk about routing SDI signals, we feed them all into one big central SDI router, and we're making cross points. They literally are physical switches on a bit of silicon somewhere, passing the signal wholeheartedly through to a dedicated output. With IP, we're passing signals along in discrete packets, and typically those packets don't fill the full capacity of those pipes. You might have a 10 gigabit pipe, and you're only using a gigabit's worth of data. So the packets are relatively small. But what it means is we can switch things at packet level, and we can send multiple signals down a wire. But more than that, fundamentally, all IP connections have two paths, a send and return. They're full duplex. Every Ethernet cable you plug into your laptop or every fiber that we're plugging in can go both ways. So as well as sending signals one way, we can send other data back in the other way. So, sorry, return signals to cameras and things like that. We can do a lot more flexibility. We don't have to have that design decision that we had with SDI about deciding where to put sources, where to put destinations. Can we afford to have a few more sources on the router or so on? It gives us a lot more flexibility because by definition, we can put anything anywhere down the wire. So when we're talking about IP for video, I showed the slide before, we're taking what was a traditional real-time continuous signal like SDI, and we're chopping it up into little packets of data and we're sending it over an IP network. So we're going from a signal interface that had a constant data rate, HDSDI, 1.5 gig a second, onto an IP network that's capable of carrying more data. So all of those bits have been squished sideways because they're kind of the ones and zeros go down the wire a bit more condensed. Now, you might also see mention of things like 40 gig and 100 gig. Where do you want me to stand, Wes? Behind. It doesn't want me in front of the screen. There we go. Terrible. I like to be free. So yeah, I mean, when it comes to things like 40 gig and 100 gig, there are essentially 4 channels of 10 gig or 4 channels of 25 gig Ethernet. So it's all, again, increasing the amount of pipes we've got. So when it comes to what data are we sending down here, let's imagine we've got some data. It might be a line of video, let's say, or it could be a file or something we need to send across a network. Typically, they're too big to send over a network, so we have to chop it up. If we're going to chop it up, we have to add some data to those individual packets to help identify it. That could be as simple as a sequence number to say, packet 1, 2, 3, 4, so we know how to reconstruct it. Wes is going to talk into more detail about 2110 and how what information we put in those packet headers at the RTP level and the 2110 level to signal what we're carrying. We then have to choose how we're going to send it across a network. And there's 2 main protocols used for sending data across a network. The one we use in the office space and around the internet every day is TCP. This is a very deterministic protocol. I equate it to a fax machine, which is lots of handshaking going on. If you need to get file from point A to point B, you can guarantee all the files are going to get transferred because there's lots of protocol level communications going on that if any packets get lost or corrupted, the protocol manages the resending of it. What we use when it comes to 2110, though, is a protocol called UDP, which is a much simpler protocol for sending data fast across a network. There's no resending of data in the basic UDP level. It's just, if you like, fire and forget. Once you've got rid of it, whether it gets to the other end, you might be able to check that it's corrupted or not and discard the packet, but there's no mechanism for resending it. Because in video, once the moment's gone, it's gone. So the whole point of 2110 standards are, how can we architect the networks to ensure that we don't lose any of those packets? And if, in the rare circumstances we do, we've got things like 2022-7, which Wes will talk about later, which can allow us to hopefully recover from those and carry on and not lose any frames. So we're going to take one of our packets of data, stick a UDP header on it. That's got port information on it, but the other bit we need is an IP address. Where do we want to send it to? You've probably all seen IP addresses before, so each of these are kind of the way IP works is a layered model. We're wrapping packets of data with headers, we're wrapping that into another header, and in the case of 2110, when we're sending it over Ethernet, so we're wrapping it in more frame headers, and sending that down a wire or down an optical link. So this layer model, you'll see this kind of structure of packets again when Wes takes over. So just to give you an idea of scale, because this diagram really is not to scale, this is a kind of breakdown of what's in the header and the amount of bytes it takes up in 2022-6. And you can see in terms of the numbers on there that actually definitely not to scale. All of those headers work out about 6% overhead for the data. So the data is much larger than the kind of diagram shows. So when we're actually sending with UDP, as well as sending to a dedicated IP address, UDP allows us to do a thing we can't do with TCP, which is called multicast. And that sends to a dedicated range of IP addresses that are reserved for this multicast operation, and a network switch therefore knows that it's to be multicasted. And there's whole protocols defined in the IP kind of world for connecting to these multicast sources. What it means is my device that's generating video, in this case a camera, can send into a network switch a multicast stream of video, and multiple devices can then do a subscribe request to that multicast. And it doesn't take any more load to the camera. That's the beauty of using UDP multicast. You can have it doesn't change the load on that camera if there's 100 items that want to see that feed. Multicast manages all that. However, basic UDP multicast, you need to be aware, it's not one-to-many, it actually supports many-to-many. So actually there's nothing inherently in the IP layer that stops another device, maybe a camera that's been in the maintenance department, from being plugged back into the network and sending on to the same multicast group. So you do have to take a bit of care with how you're using multicast. This scenario does happen. However, if you've implemented you're connecting to those multicast using what's recommended in 2110 and TR 1001, which we'll talk about later, it's recommended to use what's called source-specific multicast, where you say, I'm interested in group 239.10.0.25, but I'm only interested in it coming from the IP address that is camera 1 in this case. So you can be specific to say, I only want the one coming from that source. Look out for that if you're buying old network switches off eBay, because older network switches may not support IGMPv3. So it might be fine for doing some tests to get you started with 2110 and all working in IP, but it may not fully support and work in a scalable environment. So what are we sending? Video. What are we talking about? We're talking about television video here. So video with audio. 2022-6 often gets referred to as SDI over IP. Wes is going to talk a bit more on it in the past. Simple one RTP flow over this UDP multicast or Unicast. Or 2110, where we're splitting it all up into individual essences. And that's where I'm going to hand over to Wes, because he's going to tell you a lot more about the benefits of one versus the other, and then dig deeper into 2110. Over to you.
Okay. So, thanks everybody. So really, the key things that I think Ed has already communicated to you is that packet-based systems are very flexible. They're very dynamic. You can rearrange them to suit your needs. And they handle all sorts of different types of media. So one of the first things I really want to make sure that we understand is the big difference between taking an entire SDI signal and transporting it over IP, which is absolutely allowed. We have standards for it. It's called ST 2022-6. We do call it SDI over IP. And what it does is it takes every single bit that you would normally find on a coaxial cable and allows you to transport that intact over an IP network. So if you take a look at the diagram that we have here, what you see is that on the input side we have data, we have audio, and we have our video. Those are all embedded together and combined into a single packet stream. So the signal goes in, we packetize it, it transits through our IP network as a series of packets, and each packet is going to have either video or audio or data or some combination thereof. It can have multiple different types of data inside each one of the packets, so that when we get to the far end, all of those relationships stay the same. The way that the video is related to the audio is related to the data, such as captions or what have you, is completely the same all the way through the entire system from input to output. At the far end, if we want to manipulate it, if we want to break out the audio separate or the video separate, we simply take the signal apart using a standard de-embedder. So it's a very simple system. The big drawback to it is it's hard to process a single part of a stream. If you're only interested in the video, you have to take that entire packet stream and disassemble it to get at what you're looking for. With ST2110, each one of the types of essence flows separately. So we take our video and we make a packet stream that's only the video, nothing else. Only the actual active live video pixels are carried over a 2110-20 stream. The audio is carried as 2110-30. That's a separate packet stream. So it has different RTP addresses, different IP addresses, different ports. Everything is different about it. So if we decide to send it to a different destination, we can tell our routers and our switches how to send those packets in different directions. Similarly with our data streams, such as captions or other metadata, timing, what have you, that can be yet another packet stream, and that can go on its own separate way. So the benefit, well, one big benefit is that it's very flexible. If I just want to work with video, all I have to do is access those video packets. If I want to work with audio, all I have to do is access those audio packets. And same thing for our overhead data. The challenge, of course, is I've got to do two things. One, I've got to maintain synchronization from my input to my output, and that's the job of precision time protocol, which Ed will go into in a lot more detail. And the session description protocol file. This is a text file that describes how each one of these packet streams is formatted, and it can also talk about the relationships between the different packet streams. So as a result, with SDP and PTP, we can deliver a live stream that has video, and it has audio, and it has the associated data with it from one end of a network to another, and deliver all of those exactly as we had before with a lot more flexibility. So, 110 is the preferred method today for a lot of different networks, specifically for the reason that Ed mentioned. It allows you to break things out. With the audio stream, all you need is an audio receiver that can accept that bandwidth, generate it, and process it, and create another new stream going out that allows you to have just that amount of bandwidth. So instead of here, where I have an audio processing device that is only capable perhaps of handling, that only needs to handle maybe 3-4 megabits worth of traffic, what I need here is I need an interface that has a bandwidth of 1.5 gigabits or 3 gigabits, if that's the type of video signal I'm using. It has to take that signal in, it has to depacketize it, has to de-embed the audio. Then you have to process the audio, re-embed the audio back in the SDI, repacketize the SDI, and send it along the network. On the 2110 system, because each stream is sent separately, My audio device only needs to receive the audio packets, take the audio directly from those packets, do its processing, re-embed them, and send them along their way. So it's a much simpler system, much lower bandwidth, much easier on overall network resources. Now, there is a cost to this. First of all, I need a way to associate the different streams together. Now, that can either be done in session description protocol using the STP file shown here, or it can be done using NMOS, which of course we'll talk about later. So that's going to name the resources, going to tell us which particular signals are associated with each other from a master control system standpoint. The other issue is that because the different packet flows can follow different paths going through the IP network here shown in gray, is that at the far end, you may need to resynchronize those packet streams or the essence within those packet streams in order for you to be able to produce something that has the correct level of lip sync and what have you. So definitely a lot of benefits, but you do need to have a global perspective in terms of how we're going to manage those streams and how we're going to synchronize them when we need to do work with them. So the next thing I'd like to show is sort of an evolutionary flow of how we got from where we started to where we are today with ST2110. And one of the earliest video over IP standards that existed was Pro-MPEG COP3. That's MPEG-2 transport stream compressed video, constant bit rate over IP. That evolved into SMPTE ST2022, which now has been released as Technical Recommendation 01 from the Video Services Forum. The beautiful thing about TR01 is that not only has it been highly relevant throughout the industry, but it's just been updated to support the ultra-low latency codecs that are now available, things like JPEG XS, and et cetera. So still a very viable standard today. Another foundational document is RFC 4175. That tells us how to take pixels of video and put them into RTP packets. So a lot of the work that we did in ST2110 was built on that. Another foundational document is AES 67. That's how to take audio samples and put them directly into IP packets. So the first generation specification that we came out with was TR03, again from the Video Services Forum. It was meant to get this whole process started, and it combined the video based on RFC 4175 and audio based on AES 67. In the meantime, we also had variable bitrate ST 2022-3 and -4. We had an uncompressed video signal that came out called Aspen, also described in a SMPTE registered disclosure document number 37. That took uncompressed video, put it into transport stream, and used a lot of the transport mechanism in ST 2022. ST 2022-5 and -6, we were just talking about that. That's how we do uncompressed SDI, the entire payload, into a single packet stream. And a version of that was also developed called TR04. Now we get to ST2110. So let's look at the main parts of that, and we'll go into these in more detail in the coming slides. ST2110-10 is the system level spec. ST2110-20 is how we do video encapsulation. ST2110-21 tells us how to put the packets out on the network in a controlled manner. That's very, very crucial so that we don't overflow buffers in the network. And we'll go into that in a little bit more detail. We have ST2110-30, which is the audio portion of ST2110. That is very strongly derived from AES 67 and in fact refers to it directly. Come on and sit down if you'd like. Then we have ST2110-40. That was kind of a new development. That was how we do the ancillary data into a compatible ST2110 stream. So that is based on a brand new RFC called RFC 8331, and that is, again, that's one of the four main essence formats that we're going to be using in ST2110. Now, one standard that kind of bridges the two domains of compressed and uncompressed video is 2022-7. That's called hitless switching, and it allows you to send one stream over two separate networks and recombine them at the end to avoid having a problem with either network cause you to lose your signal. It's actually a very valuable standard, still in use today, and it can be used either for compressed or uncompressed systems. Then we have 2022-8, which is a little variation on the way that ST 2022-6 is encapsulated, and it was done to allow the 2022-8 streams to use the same timing system as 2110-20 streams. And then, of course, we have ST 2110-31, which takes an uncompressed audio stream, not individual audio samples, but the entire audio AES-3 signal and puts it out over a IP stream. And then recommended practice 2110-23 and ST 2110-22. Those are new documents. The RP-23 is how we do large format video over multiple substreams, makes it easier for some networks to handle. And 2110-22 has just been released, and that is how we do compressed constant bit rate over an IP network in a way that's compatible with 2110. So you can see, here's all the ones that were released as of a few weeks ago, and here are the ones that are imminently coming out. So we have an overview document as well that just sort of describes how all these documents fit together. We have our constant bitrate compressed video and our single video essence over multiple streams. And there's more to come. So we won't go into those today, but there's new things being worked on in SMPTE as we speak. So, system timing and definitions. This foundational document really tells us the rules that apply to all ST2110 systems. So we have a maximum UDP datagram size. Notice that there's two versions of this, like any good standard, right? We have a preferred one, which is 1460 octets, but we also accommodate jumbo frames, which are widely used in video to handle up to 8960 octets of UDP datagrams. We have precision time protocol. That's called out specifically in 2110, and that's how timing works. You must have PTP on your network to support a true 2110 based system. The RTP timestamps are tied to the media, so each packet that comes out gets a time stamp based on the PTP clock. The different RTP clocks advance at different clock rates, audio versus video, but you can relate them all back together using PTP. And one thing that's definitely specified in 2110-10 that's crucial to interoperability and quick system recovery is having zero media clock offset. And what that basically means is that all the streams in a network all need to use the same reference point for starting their RTP clocks, and it prevents a lot of issues when you have system resets and things like that. Video encapsulation. So how does that work? Well, the first thing we're going to do is we're going to come up with this concept of a P group, and that comes from RFC 4175. And a P group is really a group of pixels. What else could it be, right? So we're going to take multiple groups of pixels. We're going to apply an RTP payload header. That header is specific to ST2110, and that's going to tell us how the pixel groups inside this packet are located within the video frame that this packet applies to. Then we're going to insert this into an RTP packet. So that'll be the standard RTP header that's used for many, many applications, all the way back to Code of Practice 3. Place in a UDP packet, that goes back into the 70s, that format. IP packet header, and then we create an Ethernet frame out of that by adding a MAC header and a checksum. Now, this is a different format, but it really goes back to what Ed was talking about before. It's really the same type of information we were talking about previously. So, what's a pixel group? Well, I'm glad you asked. Pixels have to be formed into groups, and there's two rules for a pixel group. The first rule is that pixels that share the same samples must be in the same P group. So as you know, in a lot of our video systems, we use fewer chroma samples than luminance samples. So what we do is we ensure that the chroma and the luma samples that relate to the same pixels have to be in the same P group. In addition, every P group must be an integer number of octets. What that means is that the number of bits in a P group has to be evenly divisible by 8. So here's an example. We have 422 10-bit, which is by far the most common transport format, what we use in SDI all the time. And what you'll see is we have 2 pixels in 5 octets. So the 2 pixels you'll see, we have 2 Y luminance samples, okay? One shown here, one shown here. Then with those 2 luminance samples, we have 1 blue color difference sample and 1 red color difference sample. Since each one of those samples is 10 bits, what we have is 4 10-bit samples, all in the P group, and conveniently, 40 bits is evenly divisible by 8, so we have 5 octets for that P group. Now you might say, geez, this is a little hard to calculate. How do I figure out what size my P group is and how many pixels are in it and everything like that? Well, don't worry. Right in the ST2110-20 standard is a table that gives you all of that information for every kind of video format that we could think of. And there's literally dozens of different formats in there that can be accommodated using P groups and therefore placed into ST2110-20. Next thing I want to show you is just a little bit of information about the ST2110 payload header, okay? And that's this portion down at the bottom. So everything above the red line is a standard RTP header. Every RTP packet uses the same header format. Below the line, what we see are the things that are unique to ST2110-20. The first thing that we have is a high-order RTP sequence number. So that takes our 16-bit sequence number that's standard in RTP and adds another 32 bits on, or another 16 bits on top of that to give us a total of 32 bits. We do that because we would, without extending that number, we would wrap around our count every 64,000 packets, which in an uncompressed HD environment can happen in less than a second. So now what we need to do is extend that up to 32 bits. That gives us 4 billion packets that we can accommodate. So that will give us hours between when the combination of the low bits and the high bits, the full 32-bit sequence number wraps around. The next thing we have is so after the sequence number, we have sample row data information. So this is data about what's going to be inside this packet. The first thing is the sample row data length. So that's going to say how many bytes do we have. So if I had 400 P groups, that'd be a little bit too many. Let's say I had 200 P groups, and each one of the P groups had 5 bytes. Then my sample row data length there would be 1,000 bytes. So it's the length of the data contained in this packet for the first sample row. Then we have the sample row data number. That tells us where in the image it came from. So if it's the first line of video, it's going to be sample row of 0. Then we have the sample row data offset. Not all of these sample row data packets are going to start at the beginning of a video line. They might be partway through based on where those particular lengths of packets map into the video sequence. And I'll show you a picture about that in a minute. So the sample row data offset is 0 for the first set of data in a row, but after that we'll have an offset. We have a couple flags here. The F bit indicates interlaced video, as you can see over here in the legend, and the C bit tells us if we have data from more than one row in the packet. So maybe that's a little cryptic. Let's take a look at a picture. So here is my video image laid out. Normal vertical ancillary data, horizontal ancillary data, my active video, my actual pixels. So the first rule in ST2110 is we're only going to send the active video. So we get rid of all the Hank and the Vank and everything like that. So my first packet, we'll call it packet 0 because we're software guys, we like counting from 0. That's going to be sample row 0. It's going to have an offset of 0 because it starts at the very first pixel, and pretty straightforward. Packet 1 is going to be still in sample row 0 because I didn't get all the pixels in this line of video. It's still going to be sample row 0, but this time it's going to have an offset, and that x is going to be the number of pixels in packet 0. So it's going to be offset from that. So when the receiver gets it, it can put that new data in the correct place in the video raster. Then for packet 2, notice that in this case it wraps around from the first row to the second row. So we're actually going to have 2 sets of headers. We're going to have a header for sample row 0, which has an offset of 2x. Okay, so that's going to be the start of that little group of pixels there. And then it's going to have some pixels from sample row 1 with an offset, again, of 0 because it's starting at the beginning here. So on and on, we have a very simple system for precisely addressing where pixels go within a video frame. Audio encapsulation, even easier than video because we don't have a payload header this time. We just take our audio samples, 16-bit, 24-bit. Those are your 2 basic choices today for ST2110-30. We put those we bunch those up. We apply an RTP header, UDP, IP, Ethernet, and we're good to go. Now we have a compliant 2110-30 audio packet. The timestamp of the RTP packet header is going to use the sample time of that first audio sample in the packet. So again, it's very consistent with AES67. So based on AES67, 0 offset media clock, audio channel grouping we'll talk about in just a minute. There's different receiver classifications that we added in 2110. And the packet size limit adheres to the limit we talked about before with ST2110-10, 1460. We take away our RTP and UDP headers, so our payload for audio is 1,440 bytes or octets, depending on how you want to say it. So, Ptime. Ptime is a parameter that we use to describe how the audio packets are formatted, and we typically group them into packets of, let's say, 1 millisecond of audio or 125 microseconds of audio, etc. What that does is it drives how many audio samples can actually be in that packet. So the number of channels of audio is limited by the payload size. So let's say we had 1 millisecond of audio, 24-bit sampling. That works out to 144 bytes. At most, I could put 10 channels of audio with a 1 millisecond P time in the 1,440 bytes. The next slide shows the receiver classifications. And without going into a huge amount of detail, the A receivers are basically is the minimum that you can have for a compliant ST2110-30 receiver. We have extended capability there that adds a 96 kilohertz sampling. Notice because the sampling has gone up to 96 instead of 48, that I can only have half as many audio channels in there. Class B, I can have 8 channels of 1 millisecond audio or 8 channels of audio that's packed into smaller packets. So 125 microseconds of audio in each packet means that I need 8 times as many packets for each audio, but that might be good if I need low delay. BX, again, extends that up to 96 kilohertz. Note here, because the amount of data is less, a shorter amount of time, 125 microseconds, I can actually accommodate 8 channels of 96 kilohertz audio. And then the Type C receiver was designed specifically for compatibility with things like MADI, that we use a lot in audio. So this can handle up to 64 channels of audio using 125 microsecond packets and 48 kilohertz sampling. If you go to 96 kilohertz sampling, you need a CX receiver, and you need you can only handle 32 channels. The last big thing that we did in 2110-30 was we added some metadata for grouping channels together. So instead of just a whole bunch of mono audio channels, we have stereo, we have dual mono, we have matrix stereo, surround sound 5.1, surround sound 7.1, surround sound 22.2, and of course, being a normal standard, we have an open-ended one. So if you have if you need 7 channel or 13 channels of audio, you can also specify that using the metadata for ST2110-30. 2110-31 AES-3 audio streams. A lot of times AES format is used for things that are not PCM audio, so they don't have 8-bit or 24-bit samples, so we need a way to transport those transparently across an IP network. And note that you should not be using 2110-31 for good old linear audio. So how does this look? Basically, very similar to what we've seen before. We have a RTP header here. We have and then immediately after that, we just have 32-bit subframes based on a MIME type of AM824, MIME subtype, I should say. That includes 24 bits of data plus 8 bits of overhead. So very, very simple format. So the next thing we want to do is, and the last thing I want to talk about in this section, is 2110-40 ancillary data, all the good stuff that comes with video that needs to go over ST2110 as well. Well, the good news here is that that data is already formatted into packets. And you can see the packet format here. That's right out of the SMPTE standard, I believe it's 291. You take those ancillary data packets, you get rid of the header that was required in SDI, but you keep all the rest of it. So you keep the data identifier, the secondary data identifier, the data count, the user data, the checksum, all of that information that comes to you natively in SDI remains exactly the same when we convert it over for 2110-40. But then, of course, we need to add a RTP header. So that's going to have our sequence number and SSRC, just like all the other RTP headers we had before, and I'll show you that in a minute. We have our payload header, and then we have our special header for each packet of data within the 2110-40 subsystem, and that gives you the line number and the offset. So this information here in this blue rectangle tells you exactly where this ancillary packet would appear inside the SDI raster. So it tells you the line number, and it tells you the offset. So you see a pattern going here. We're always going to be talking about line numbers and offset. The one difference is that with 2110-40, the line numbers that are carried in this field apply to the SDI signal. With 2110-10, we only care about rows of pixels, so that the row numbers that are in the SRD data do not match the line numbers that are in the ST2110-40 individual packet subheader. So, ancillary data packet format, we start out with a line number and an offset again, so we can tell where it came from. We have a flag if we're using a multi-stream environment. We can set the stream number there. This data comes directly out of the packet that came from our vertical ancillary space. So the DID, the SDID, the data count, those are all 10-bit numbers. We kind of put them in there. Then we have the actual contents of the ancillary data packet. Again, all 10 bits of every field within there. We have our checksum, which is 10 bits. Now, because this is all 10-bit data that you see here, it might not line up evenly with a nice count of octets that we need for IP and UDP and all the other layers down below of the IP stack. So we actually put in a little bit of padding to always bring that up to exactly 10 bits. I mean, exactly 32 bits. So, SDP, Session Description Protocol, that little file that I talked about, that allows us to describe how the video is formatted and all that other good stuff. Well, with STP, that's also based on an RFC that's been out for a while, 4556. And this gives you the key data that you need to process that video content. So how is the stream structured? What is the connection information? What are the IP addresses or the multicast addresses for these streams? Does the signal relate to clock and timing? The beauty of STP is that it's a text file. So I could literally take an STP file and deliver it to you as a piece of paper. I could send you a fax, believe it or not. I could move it on a thumb drive. Obviously, the preferred way to do this is to share these files using NMOS and ISO 4 and ISO 5 and all that other good information. But it's a text file, so there's lots of different ways of transporting it. What does a session description consist of? We have session information, we have timing information, we have media information. Those are all required, so that tells us about the session in general, and I'll show you an example in just a sec. Shows us the timing information for this particular session. The media information, so how is the video or the audio formatted. And then we also have a required connection information field that either has to be associated with the media or associated with the session. Must have it, but it can be in either one of two places. So this is what STP, a very simple STP file looks like. They all start with v equals 0. We have some information that basically names and describes the stream, the O and the S fields. We have our timing information. Then we have our media definition. So in this case, this is a video signal that's being multicast on a IGMP v3 multicast, so I have a source filter applied here. It's a 90 kilohertz clock for the video. And here's all the good stuff about the video. It tells us that it's 422 video. It's 1920 by 1080. That it's interlaced, so it's a 1080i signal. Frame rate is 30,000 divided by 1001, so that's a 29.97 hertz sampling rate. Therefore, we'd probably be using this signal in North America or Japan. 10 bits per sample, our standard colorimetry, SMPTE standard number, etc. And then this is the information that tells us where the clock that was used to generate the RTP timestamp for this stream. So, without going into a huge amount of detail, for every ST2110 stream, whether it's -10, -20, -30, I mean not -10, -20, -30, -40, -31, any of the new versions, you're going to have an STP file, and they're going to look something like this. So, down at the bottom here, we're talking about PTP. Well, let's figure out what PTP is, and for that, I'll hand it back over to Ed.
Thank you, Wes. And Andy's given me a magic pill for my throat, so hopefully I won't be coughing too much this time. We'll see. So, time. Time's always been important in broadcast and media production. Different people, depending on the use case, talk about time in different ways and what they mean by time. Across broadcast, some people care about dates and times of day. If you're capturing lots of raw footage and you might want to be able to edit it later, capturing that time code is important. If you're working in a studio environment and passing signals around a facility, typically you're caring about frequency and phase. You're caring about the gen lock of your system. Are all of the cameras that are generating 25 frames a second generating it to the same concept so that all the frames line up together and stay lined up together throughout the production. And there were many standards for synchronizing your systems and to keep track of those time codes. Now we can do all of those that whole scope of from dates all the way down to kind of very fine phase alignment with a new standard, well, not a new standard, old one called PTP. So Precision Time Protocol. It's built upon a protocol that's from outside broadcast. This is a kind of worldwide, a protocol defined by the IEEE. It just provides a mechanism for setting clocks very, very accurately via some defined messages, and that's what we're going to be talking through. Now, the timestamps themselves within those messages to kind of give you that clock resolution are 48 bits of seconds and 32 bits of nanoseconds. This gives us a lot of high precision very accurate level of, down to nanosecond accuracy of what the time is now. And with the performance of a PTP-based system, we typically talk about a kind of sub-microsecond accuracy. If you were kind of compare that to kind of what came before the older NTP standard that your Windows machines used to synchronize clocks, and many systems in broadcast facilities already use NTP to synchronize time across systems. With that, you're talking down to kind of 200 microseconds. So a couple of orders of magnitude in terms of difference for the accuracy of what the clock resolution can be. So it can do everything all the way up to kind of dates and things in those PTP timestamps because of those 48 bits of seconds. We've learned from Y2K, there's no rollover problem going to be coming for another 9 million years. So, the PTP timestamps are not going to be a problem with rolling over. So, at its very basic level, in a PTP-based system, you have a grandmaster that knows the time. Typically, they have a GPS antenna to get the very accurate time. They can be free-running, but in a small test system, but typically they'll be GPS locked. And then you have some slaves, and then you have some network connectivity between them that passes messages, and it synchronizes those times on all of those slaves. Now, the beauty of PTP is that even if you've got a slave down the end of a very long wire, or through lots and lots of network switches, and the messages take longer to get there, it still knows what the time is. So the way fundamentally PTP is doing this is it's sending out messages saying, the time is 12 o'clock. And someone over there is listening, going, okay, I'll set my clock. Now, things take time to propagate across signals. So if you've got someone who's further away, it's going to take longer for that signal to get there. As long as they know how long it's taken that to get there, they can adjust for that and very accurately set their clocks. And that's fundamentally what PTP is doing. The problem is there's lots of different ways to configure the systems in a PTP network as to how to work. And then once you've decided what mechanisms you're going to use, you need to discuss how many messages per second you're going to be doing. Are you going to do 8 of these messages a second, or just 1 a second, or things like that? You've got to decide all this. And this is where a lot of the problems in IP-based systems are coming, is because people aren't defining this early on and aren't thinking about it early enough. They just think, oh, we've bought a PTP grandmaster, we'll plug it into a network and it'll all work for us. And that's where people are falling down. So if we look at what's going on between a master and a slave on a PTP network in terms of the messages that are going back and forth, in its simplest form, the messages would look like this. Coming from the master, a sync message. The time is 12 o'clock. I'm sending that out. The slave receives that, and then it knows it received that at what it thought was, well, I thought it was 11:58, but okay. At 11:58, you told me the time was 12 o'clock. Great, okay. Now let me figure out how long it takes the messages to get between master and slave. So I'm going to send out another message, and I'm going to know when I send it. I'm going to send out, I want to know how long this message takes to get to you. Right, that was at 12:59 by my clock I sent that. Okay, I've sent that out. That's T3 on this marker. I apologize, they're a bit small, but I made a poor choice in the angle that I chose when I drew these diagrams. The PTP master receives that message, and it very accurately records its time that it received that packet, and that's T4 in this diagram, and it sends that T4 message back. That sending it back is a less time-critical message. But once all of those values get to the slave device, it's got enough information from those 4 values to do a bit of algebra. It's very simple maths, and from that it can work out what the offset is from the master clock and how long it took the message to get there, and it can therefore set its clock very accurately. So this delay request and response messages is key to what we call the end-to-end delay mechanism. Now, that whole process started with that sync message. The time is 12 o'clock being sent in a message. If we're a software-implemented PTP master, and we're saying, right, I'm going to format a message and I'm going to put the timestamp of 12 o'clock in it, I'm then going to hand that over to the hardware layer to put all those extra, IP wrappers on it, the MAC layer wrappers on it. It takes time to work through a system to get out onto the wire. And because of that time, that introduces inaccuracy in that time. So what some systems do is either redesign it at the hardware layer so that they can insert that timestamp very accurately at the point that it leaves the device, and that's called one-step mechanism, because it's able to do that. But what many other systems do is realize, okay, I'm never going to be that accurate, so what I'm going to do is ask the hardware layer to report back to me when this packet leaves, and then I'm going to send a follow-up message to say, actually, that packet that I just sent to say 12 o'clock, it actually left at exactly 12 o'clock and a little bit more, and it gives a very accurate timestamp in that sense. So you'll see more diagrams commonly drawn like this, where you have that initial message, there's an extra secondary follow-up message. And all that's doing is it's because of that inaccuracy, that inability to put a very accurate timestamp in that first sync message. So that's why we've got this second green line. It's basically reporting back from the hardware layer and saying, actually, that was the time that packet got sent to you. So otherwise, the maths is exactly the same. So you might see this discussion of one step or two step, and it's all down to how accurately the hardware layer can insert those timestamps. So in a real system, that looks like this, you've just seen there's more messages going back and forth, so I could draw some extra lines on here. By drawing lines like this is implying unicast. Now, actually, this is not the default. Most systems work in a multicast way where everything goes to everything, and everything can hear that, and they just have to ignore it. That can, again, cause a lot of overload. If you've got over 100 devices that need to talk PTP in a network, possibly that's too much than one grandmaster can cope with, and you need to take some design choices on how you can go beyond kind of that scale. Another way you can change the configuration and reduce the load on the master a little bit is, rather than sending unicasted messages to each of the individual slaves, you can send a multicast instead. So we can say, at that time now, I can shout to everybody rather than shouting it into, unicasted to one specific person. And again, so you could see this called mixed mode. Some people call hybrid mode. So again, that sync and follow-up message is multicasted, whereas you might use unicast for the rest. Multicast, though, is the default, and that's often the most likely to cause you problems, and that's why people are shying away from it and moving on more onto mixed mode. And of course, in reality, we've got a network switch in the way. It's never really a point-to-point wire. It's, we've got to go through a switch. So how does that network switch cause change the way the packets behave through the network? So exactly the same diagram as before, but I've stuck a network switch in the middle. The network switch is dumb. It's just forwarding packets to the destination, or forwarding multicast packets in standard IP ways. Nothing's changed. It's just there's this network switch in the way. Now, network switches have buffers internally. They have message queues. They introduce latency. And that latency is variable. Sometimes, if there's not a lot of traffic on the network, it'll get through the network switch really quickly. Other times, it might be delayed a little bit, and it might take time. Now, this end-to-end model that I talked about, this delay request message and the delay follow-up message, and then the maths that all fall out of that equation, it only works on the assumption that the round trip time, the time it took to get from slave to master and back again, is symmetrical. So if on one pass it took longer in the network switch and on the other pass it took less time, the maths are going to introduce some slight errors, and that can introduce jitter. And that's kind of one of these areas why in a lot of network design, people are being pushed into having PTP-aware switches that do something a little bit cleverer than this. So you can use passive switches. You just have to be aware that they can introduce jitter. And again, people who are designing systems that are PTP-based can work around that by smoothing out the timing reference over a few packets and very accurately get a very accurate clock from it, even with that jitter. But it depends on how well that iteration of those packets is implemented and how accurate it can smooth it out. So in the EEE 1598 standard, there are 3 devices specifically defined that relate to the way those network switches can behave. That's what I've drawn in the green box here. Just for clarity, everything else in a PTP network is called an ordinary clock. So the things I've been talking about, masters and slaves, these are called ordinary clocks. It's just they're either in a master mode or they're in a slave mode and things. And by default, an ordinary clock can change roles and it can become either. And in fact, that's part of things like TR1001 we'll talk about later. It's very important that if you've got a camera, you tell it that you are only ever going to be a slave. Don't ever, the underlying PTP libraries, if they've been implemented just by taking a standard set of libraries, they might have the ability to become a master. And that you don't really want that. You don't want don't want the master accidentally kind of handing over to something it shouldn't be used by. So at the network layer, we've got 3. Boundary clocks and transparent clocks, and in the transparent clocks, there's two different variants of them, and it all comes down to how we measure this delay. The boundary clock is the easiest to understand. And actually, this is really good for architecting large networks because it allows you to get beyond the limits of what one master can serve. So with all these messages flying back and forth, a master clock can only serve so many slaves before it just gets overloaded with work to do in terms of responding to all these delay requests and things like that. So boundary clocks are useful for segmenting networks and growing them. Essentially, it's as I've drawn here. You've got one port on the network switch will become the slave, and all of the other ports on that network switch take the role of master. And internally on the switch is some code in either software or hardware that's implementing PTP ordinary clock mechanisms on each of those ports. So how would that look? Drawing it, I've kind of shown them very synchronous here. Obviously, that in reality, it probably they wouldn't be quite so nicely aligned, but there's two independent discussions going on. There's the upstream kind of discussion, synchronizing the first master that's in that boundary clock, and there's all the downstream discussions to all the myriad devices that might be other network switches and other boundary clocks, because this can be all through a big tree structure and to distribute time, but it's all independent. And again, using that delay response mechanism through that. With transparent clocks, the sync message that comes from the master is going straight through the switch. So unlike the ordinary clock where it's essentially taking the place of a master, in transparent clocks that sync message from the grandmaster at the top here is going all the way through the switch. It's not transparently though, it's actually the point of a transparent clock is that it can modify it as it goes through. It can add some extra information to it to try to help the system understand about the delays that are being introduced by that network switch, and that's the key. Because of that, that's where the jitter gets introduced in a system, is because of the variability in a switch. The two variants of transport clocks are down to then how the slaves themselves work out the overall delay that they have to put into the maths equations to figure out the offsets correctly. So we've got to talk about these mechanisms. That delay request and delay response message I talked about earlier was called end-to-end. The slave sends it, and the master responds, and it works it out as a full round-trip delay through the whole system. Nice and simple. Peer-to-peer mode is the same kind of mechanism, but instead every little element on the network has got the ability to send and receive these messages just back and forth down its local wire. So from me, the slave, to the network switch port, I'll be using the same kind of mechanism of messages to just work out the delay on the wire. And each point of the chain will do this, have implemented the same way. So in a transparent clock end-to-end, again, message comes through, goes through the network switch onto the slave. Again, apologies that text is very small. Hopefully, if YouTube HD is good enough, you might be able to put this full screen and just about read it. PDFs of these will be available to download on the IP Showcase and VSF website as well, so you can get all of these pictures hopefully soon after the show. Now, importantly, that transparent clock is measuring the time it takes that packet to go through the switch. So when that sync message comes from the master at the top here, comes traverses across the wire, and then goes into one port, spends some time in the buffers, and then leaves through the other port, it very accurately records the time it's spent in the switch, the residence time in that switch. Now, if it's able to, remember the one-step, two-step discussion, if it's able to, it can put that time directly in the sync message as it leaves it, in that kind of one-step mode. More likely, though, is it does it as to the follow-up message. When the follow-up message comes through, it goes, that follow-up message relates to that sync message that just went through a moment ago. I'm going to add that residence time into an extra correction value. If we, just like with the 2110, if we looked at the headers, you'd see that there was a separate point for the that correction field. Again, it's much like a PTP count, really. And it tells you how long it's spent in the network switch. It's as simple as that, really. Now, on the return side, when we're doing the end-to-end messages, the switch does the same thing. It measures the time, because this red line is time critical. It measures the time that red line spends going through the switch, and it does the same thing. When the response comes back, and again, there's a bit longer time implemented here, so this can be a bit harder for a network vendor to implement, but because they have to keep track of that residence time. And when they see that response message, again, they add that into the follow-up. So if you could read it, it says correction here. It's added some extra data. It's modified the packet, essentially giving the slave more information about that variability, because the wire speed doesn't really change. It's the variability. Did you need to ask a question? Yeah. That's right. Yeah. Sorry? Yeah, yeah. So the question was, we typically in broadcast care about accuracy down to line level when you're timing into switches and things, vision mix and things like that. Is nanosecond accuracy really needed? No, we don't need nanosecond accuracy. But no, it isn't. You're quite right. But where it matters is that gen lock. It's getting the phase alignment of your signals, and it really needs to be down to line level in most cases. But when we're also using this to synchronize audio systems that are down to very, sub-millisecond accuracy on this. It's just a standard that's capable of doing very high resolution, so it suits our needs. In reality, if we implement it well, the clocks, they'll be more accurate than we really need. But the whole point is, if you don't implement it accurately and you do get variance, that variance could increase over all the network steps. So if each of these transparent clocks didn't accurately do its job, from the top to the bottom, if you had 5 layers of boundary clocks and transparent clocks in there, you could insert more and more variance, and you might end up with big problems. And that's where a lot of projects have had trouble, and a lot of the test and measurement people have got various tools now for looking at that jitter on the PTP. And again, it's modifying the values as it comes through. Peer-to-peer mode, as I said, it implements a different messaging exchange to work out the time on the local wire. So these blue and purple messages, it's using the same sort of maths as that first diagram we looked at to work out the local delay on that wire, and then the network switch is doing that previous trick of adding the residence time and the time it knows about its upstream wire delay. So again, it's trying to help the slave have all the information immediately, so it doesn't need to mess around with that end-to-end model at the end. So this diagram is all the signals that you need. There's no, it's not just because I've not got space at the bottom to draw the older, whatever color it was, red and orange ones at the bottom. So it's a different mechanism. So as you can see, there's lots of choices on how to implement it, and that's where a lot of the problems in projects have come from, because you've got to figure out how you're going to implement these and stick to it. The other thing in a real network, you're typically going to have 2 masters for resilience. And there's how do you choose which master to use? I mean, hopefully they're both locked to the same GPS satellites in the sky, and they would be the same time anyway. But 2110 kind of dictates the use of the best master clock algorithm that's part of EEE 1598 that determines which grandmaster is the most appropriate to use, and that kind of gives you that mechanism for how to do it. So when we look at signals, again, without a PTP connection at all, which really shouldn't be happening, there's no concept of time, really, in terms of frequency. So the concept of 25 frames a second may be different. It's non-synchronous video. So, of course, just like applying a gen lock, we apply a PTP sync to it. I mean, it's on a network, so it just connects to it. But it means that all of your signals are now nicely aligned. All the cameras can be outputting line 1 at the same time and so on. And hitting the network switch at the same time and all your downstream equipment. But of course, what happens when you hit a network switch? I already kind of mentioned that switches have internal buffers that modify this, have to delay the signals. And if we look at a switch where we might want to take feeds from cameras down to a vision mixer or a multi-viewer, we're going to have to put those packets into a buffer. And on the output of that buffer, we can't write them all out at the same time. We have to wait. So this buffer that I've kind of drawn here, this has kind of got what you sometimes refer to as the leaky bucket model. You're putting packets in at the top, and you're feeding them out at the bottom, like a leaking bucket. And there's the potential, if you put too many in at one time, you can overflow the bucket. And that depends on how big that buffer is. So you'll see a lot of switch manufacturers saying, oh, you should use this network switch for media networks. They've got very large buffers that are shared amongst all the ports. Because, of course, if we have packets that aren't so nicely timed, that buffer gets hammered. And the time that the packets are then coming out on the output side, down that wire, if you actually look at the inter-packet timing, it's completely different timing. You've introduced jitter, essentially. So again, this is where some of the latencies become involved in all this, and why it's important to have standards to define how the packets are sent across the network. So these are some Wireshark captures. I took an interop a couple of years ago of data on a network. You can kind of see the characteristic gaps of of every, the VANC data gaps, if you like, of data. But not all devices send on the network in the same way. And that's what Wes is going to talk about now. It's key to the 2110-21 standard. Wes.
So, hello? Okay, 2110-21 traffic shaping. So, the idea here is that we're going to have a standardized way to push packets out on the network. And like Ed mentioned, we're going to be using this concept of a leaky bucket. So we generate packets, we put them into a buffer, and then we drain that buffer to send them out on the network. Now, every ST2110-20 sender has to be compliant with ST2110-21, which is the standard that tells us exactly how we're going to push packets on the network. And there's two models you have to comply with. The first one is network compatibility. This is designed to ensure that we don't overflow the buffers that are inside the network equipment. So here we use a drain rate that's roughly 10% faster than our video rate. So that makes sure that our buffers are constantly getting cleaned out inside our network equipment. The other thing that we have is a virtual receiver buffer model. That tells us how quickly the packets are being absorbed at the far end. Now, this particular buffer, we never want it to overflow, but we also never want it to underflow. So this has different constraints on it, but it's balanced perfectly to the exact video rate. So if our sender obeys the network compatibility model and the virtual receive buffer model, then we will have a system that's compliant to the standard. Key thing in the read schedule, the virtual receiver model, is that we have two different modes. We have a linear mode, which means that the packets are evenly spread out over the duration of a frame of video. And then we have a gapped mode, which means that packets are being sent at roughly the same time intervals that we would see pixels in an SDI. So we would see packets come out, then we would, for a while when video was happening on an SDI, then we would see a gap that corresponds to when the vertical ancillary space is. So actually, the gapped model is preferred. It makes the ST2110 sender more compatible with existing SDI senders. So we have three different sender types. We have the narrow, which is gapped, so that I send packets for a while. I take a gap during my vertical blanking interval, then I send packets for the next frame. I have narrow linear, which means that the packets are just continuous, corresponding exactly to the duration of the video time. And then I have wide. Wide allows us more variation. The packets can be bunched together more, spread apart more. That was primarily designed for software-based senders that might not have really good control over their network interface. We have sender and receiver compatibility rules in 2110-21. We have a narrow synchronous receiver that is only required to take a type N sender, which is just the narrow gap sender. And it's optional to absorb the narrow linear sender. Synchronous wide has to handle all of the types of senders we mentioned before. Type A, the asynchronous one, has to handle all those different sender types without having the benefit of having an absolutely synchronous reference clock associated with it. So you might think of this as being like a receiver that includes a frame store in a current SDI type of environment. A couple new parts of ST2110. ST2110-22, professional media, constant bitrate compressed video. So keyword constant. Typically, this standard is designed for visually lossless compression. The one that's totally released today is VC2. That's the Dirac codec that was pioneered by the BBC a number of years ago. That's described, the RTP encapsulation is described in RFC 8450, and JPEG XS, which is proceeding rapidly through the IETF's process and should be an RFC soon that allows us to also have JPEG XS as a permitted RTP standard. And these video compression systems will typically give you a 2:1 to 8:1 compression, but you could take a 1080p signal, fit it into a gigabit Ethernet. That's a pretty powerful capability. When we create the STP for this, we add a couple of new parameters. One of them is the bit rate that tells us how much compression there is on this particular system. And we also have two different ways of expressing the frame rate. One is a decimal number, the other, just like in ST2110-20, which is a ratio of two integers. There's a new recommended practice also coming out. That's what the RP stands for. That's how we take one video signal and put it out over multiple streams. The primary reason you'd want to do this is to get signals to fit onto narrower bandwidth network pipes. So there's three methods defined to split the stream up. One is called temporal deinterleave. So let's say we were running something here at, let's say, 240 frames per second. I could make 4 60 frame per second video streams out of that. Each one of those would be ST2110. The second method, which is deprecated and may not end up in the final version of RP 2110-23, is square division, where we take our image and divide it into 4 sub-images. That's kind of hard to get the sub-images to be ST2110 compliant. We do 2 sample interleave. What we do is we take groups of 2 pixels and sort them into 4 different pictures. That's very handy because it allows us to have each one of the sub-images look very much like the original high-resolution image. And again, those 4 images can be spliced together and made into the full high-resolution signal we saw before. 2022-7 redundant transport. Basically what we're going to do is we're going to send an identical signal over 2 paths, path A amber, path B blue, and we're going to, in the destination device, we're going to resynchronize those 2 packet streams according to SMPTE 2022-7. And this is a diagram of kind of how that works. We have our packet source sending out packets, but you see when they get to the destination that my packet numbers are not aligned. So what I'm going to have to do to read those packets out is I'm going to have to align the packets based on their RTP timestamps. And I'm going to be able to dynamically switch from one stream to another in case of an error. So in this case, I got packets 99 and 100 from the green west stream. Packet number 101 was an error. So at my output, I switched immediately over to grab packet 101 from my blue east stream, and that makes up my output. Then packet 102 had packet 102 had a problem in the blue stream. So I immediately switched back to the green stream to pick up packet 102, put that on the output, and now I'm reading packet number 103, so I need to decide which one of those I'm going to use and send out. Very simple, very elegant, provides a lot of benefit for not only wide area networks, but studio networks with a lot of redundancy in them. So Ed is going to get up here and talk some more about TR1001 and NMOS.
Okay, thank you. So yeah, only 10 minutes left now, so not long left. Before we talk about TR1001, I thought it's worth going over some of the standards bodies, and you keep hearing lots of acronyms and letters and body names and stuff. I think it's worth clarifying who's who. In our industry, we have 2 standards bodies, 2 main standards bodies, SMPTE and AES. AES standards are really easy. They typically are prefixed AES 67 and things like that. So SMPTE, you've seen all of these today, ST 2110, RP, recommended practice, all these documents that SMPTE put out. You then have people like the EBU that represent a lot of the major European broadcasters. AMWA and VSF are kind of industry associations. We're more focused on the kind of workflow side of things, and VSF were about moving video around across large areas. But again, these are where a lot of the work has been done that is essentially kind of percolated down into the SMPTE committees to make 2110. So, when 2110 was launched a couple of years ago now, people were already using it because it was built upon things like TR03 that VSF had written down. A lot of the work that I'll be talking about in a minute has come out of AMWA for all the NMOS protocols. And again, we're very careful to talk about them as protocols or specifications, because it's then down to the standards bodies to write the kind of committee-based agreed standards. A lot of what we're doing, though, in terms of our standards work, is built on wider standards that were defined outside of the industry. So you heard Wes talk a lot about RFC 4175 was the foundation of what's become TR03, and that's the foundation of what's become SMPTE ST 2110. IETF are the standards body that defines all the standards for the internet. So all the IP packets, all the RTP packets and things that we were talking about, all these RFC, stands for Request for Comment, which kind of sounds like it's just a proposal, but it's actually, that's kind of considered the kind of agreed standards. And IEEE is, again, another standards setting body. Institute of Electrical and Electronics Engineers. You then have other bodies like AIMS and IABM who represent manufacturers typically, but you can have some broadcasters in them. Again, they're really more on the marketing level and providing education. And again, people like AIMS are setting roadmaps and agreeing where their members have agreed that they want to indicate that they go. And TR 1001, which I'm talking about, is now part of the AIMS adopted roadmap. So again, this is why it's important. So who came up with TR 1001? It's a group called the JTNM. Where do they fit on here? Well, that's just a collection of people who work in these kind of other working group bodies. So it's more loosely kind of formed kind of group. I think they get together periodically throughout the year and talk about these things. So the TR 1001 actually kind of built upon some work that was first done a couple of years ago, but it's essentially a document that says if you're really going to make a good IP-based media network, what does it need? It needs to implement PTP in this way. It needs to implement 2110 with these constraints. You know, if you're going to do audio, it should be this classification of receiver as a minimum. You've got to support NMOS and all this stuff. It defines all of that. It's freely downloadable from EBU's website. Oh, sorry, JTNM's website. There's a link on here, but you'll find it very easily, and you can get some links at the back as well. A key thing it's built on, you'll see this a lot, is the EBU's technology pyramid that they published last year that talks about all the kind of standards and the protocols that we need in an IP media network. So at the top of the pyramid, all the kind of transport standards. These are quite well defined and quite well implemented. It may be green though. There's not, you know, it's not perfect. There are still some challenges with getting some of this interoperability to work, but it's pretty good. Then there's things like timing and sync and discovery and connection, the things that make a system actually usable without having to manually configure everything. With, you know, no one wants to be typing in IP addresses and things. They want to just have a system that is managed. And down the bottom, the real foundation of this, you need to be able to configure systems, but more importantly, systems need to be secure. So again, this is why it's the foundation of the stack. Everything must be secure by design. And EBU's done quite a lot of work on documenting cybersecurity kind of questions that customers can ask vendors, you know, can you answer these questions for us? So if you're doing an RFP or any sort of project, get hold of one of those documents. If you're looking to buy any IP equipment, get your manufacturer to give you a statement of whether they adhere to those recommendations. They're a set of very challenging questions, but manufacturers only need to write the responses once, and then they can give those responses to everybody else. So they're an important set of standards, again. So the color coding of that, you'll see some case kind of indicating that obviously we're more mature now in terms of the work on the top of the pyramid. Some people find that a little bit contentious, putting security with a red color, so you might see some people kind of take the colors away and just make it all blue and not even kind of cause that worry. Again, it's important just to highlight that these standards available. So a key part of it to make a media network work is NMOS. This has come out of the work from AMWA, which again came out of JTNM-based work called the reference architecture that was published 4 years ago now at IBC, 2015. And these are all open. You can go to the website and see them. The ones that have had the kind of most work are ISO 4 and 5. ISO 4, discovery and registration. How do you identify things on a network and find them? So it's a set of protocols about how devices should work on a network. It supports a mechanism for finding each other on a simple point-to-point connection, but what we're talking about is through a central registry, so a piece of software running somewhere. Can even run on a network switch to hold a central registry of devices. So you turn a camera on, it registers a node. In that node, there's a logical device that's providing the camera functionality, and it's going to generate video, so it's registering a sender. Other devices are going to register in similar ways. It's not a one-to-one relationship, so a device can have multiple receivers or multiple senders, or it can have both. A broadcast studio camera is going to both send video out, but it's also going to receive video for the return video. And more complex devices may have much larger combinations of receivers and senders. And some devices, maybe software-based systems or card-based frames, may actually register a single node, but spin up different logical devices on that system. And again, in the NMOS registry, there's lots of unique IDs, and lots of the interoperability testing work is to look at how this can actually scale to much larger systems. A big thing that Wes talked about as well was STP files. The streams we're talking in 2110 are not really fully self-descriptive. You need to load that little SDB text file to fully understand how to connect to the flows. So again, ISO 4 defines how that all the kind of nodes should expose these for all of the sources they generate. But then how do we make this useful? Why is it useful? It means that control systems can talk to that NMOS registry, and they can provide you details of what's on your network, and they can expose it to you. More importantly, though, with the addition of ISO 5, good old router control type systems, you can start actually having some user interaction to say, right, this node that's over here on the left, I'm going to press some buttons on my touchscreen, and the control system's going to talk ISO 5 to those things, essentially exchange the SDP type data and get that receiver to connect to that sender's flow. It could also update the sender, so it could automatically change the multicast addresses it's using, possibly even more changing parameters in future. So there's still work ongoing in that, but there's demos, I think, on the back where you'll see some of that working. Another one which I'll skim over very quickly is ISO 6, because Rob's about to give a much more detailed presentation on it. This allows us, in a larger system, rather than using standard IGMP to manage multicast or a big, large network, you might have an SDN layer that essentially sets up all the network switches and says which kind of flows to send down which pipes and all that stuff. ISO 6 is a protocol for control systems to talk to that SDN in a vendor-agnostic way so that it can make those requests for getting a flow from this device on this side of the network to that device on the other side of the network, and it all sets it up in a very standard way. Like I say, Rob's about to talk a lot more about that. ISO 7, event and tally. Think of this one like a GPI for the IP world. In its very basic form, it's just a simple trigger to say, you know, I'm going to send a message, a very time-critical message. There's a couple of different mechanisms for sending it using different very modern protocols like MQTT, which is great for broadcasting messages out to multiple devices that are interested in it, or WebSockets, which are more point-to-point. Miroslav Giras from Pebble Beach gave a good presentation yesterday, I think, on it, which will be on the website, so do look at the schedule. You'll be able to watch it back, and it goes into the use cases for ISO 7 in much more detail, but you can kind of see some of them there. And you can go to the website and find out about all the work that's ongoing with the NMOS group. There's some important ones on there about associating groups together. So if you've got video coming from a camera and it's got onboard audio, well, actually, you've got a way to signal that those streams are associated. So again, there's BCP02 specifies, add this bit to the SDP file that gives you a hint to say, actually, this is from the same logical device, and then systems can know to use them. The other bit you'll see around the show, you might see these little symbols. Obviously, interoperability is what it's all about. So the guys from the EBU and BBC R&D put a lot of work in for the last few months to put together some very detailed test plans under the heading JT&M tested. They did this again before NAB and tested really the 2110 interoperability, but just before IBC they tested NMOS and more TR1001 interoperability. There's some of these leaflets, you can find out a lot more details at the back, but it's all published in terms of who worked well together, what worked, and it, funnily enough, it didn't all work. Not all vendors have implemented things correctly. Some have. There's a lot of good news as well. People are getting there. But by doing tests like this, we're identifying what doesn't work. And you can get all of that. It's freely downloadable. It's worth picking up one of the leaflets so you don't forget it. But you'll find a lot of information. You might also see the Buy NMOS Here symbol. Again, this is just vendors who are kind of signed up to support NMOS. It's not a particular certification program or anything. So it's been a long session, 90 minutes. Thank you very much. Sorry, Rob, to keep you a couple of minutes, but that's us. So thank you very much.
Thank you, Ed. Thank you, Wes. Unfortunately, we don't have time for questions, but both Ed and I will be here for the next few minutes. So if you need to talk to us, that would be great. And we'll get switched over for the next two speakers. Hold on.